Welcome to video number 95 of the channel MALACHEMPHILIC. Video number 95 is the 36th episode of Chemical Thermodynamics, and the topic is second part of entropy, where we will discuss definition and formulation. So let's start. In my previous video, I have discussed that significance of entropy, where you have seen that you have told that entropy is the measure of disorderness. Entropy is the measure of disorderness. Means when the randomness or disorderness increases, entropy increases. And there I explain that randomness increases means the number of microstate increases. Number of microstate increases means number of arrangements of the particle increases, then entropy increases. Number of microstate is more means entropy is more. So probability of existing in more number of microstate of a system means entropy of that system is more. That is the randomness is more. Okay. Now, and all of us know that all spontaneous process, in all spontaneous processes which are irreversible, entropy increases. That also I told you that all natural processes are spontaneous. Spontaneous means occurs without any external aid. Okay. And we know that spontaneous processes are irreversible. Spontaneous processes are irreversible. Means it cannot be reversed back easily. Okay. And entropy increases. Entropy increases in all spontaneous process. Spontaneous processes. All these things we have discussed with example in my previous video. Link is given in the description box. Now, before coming to third law of thermodynamics, we should know that absolute value of entropy, that means entropy is denoted by S, this absolute value cannot be determined. Okay. Entropy concept has come from second law, but here absolute value of entropy is not determined. Absolute value of entropy is determined with the help of third law of thermodynamics. So till now what we can measure? We can measure the delta S, that is the change in entropy. This change in entropy can be measured. Okay, during a process, what is the change in entropy? That can be measured. And this change in entropy is, which is denoted by delta S, that delta S is the entropy in the final state minus entropy in the initial state. Okay. And you have to remember that for any spontaneous process, delta S change in entropy greater than 0 for spontaneous process. Spontaneous process. That means in spontaneous process, entropy increases. Why it increases, that I discussed in my previous video. And for non-spontaneous process, entropy decreases less than 0. This is non-spontaneous. Spontaneous. And change in entropy is equal to 0 when for reversible. That means when the system is in equilibrium or reversible process. Okay. Now for chemical reaction, this change in entropy, delta S is the entropy of the product minus entropy of the reactant. Now, what are the other characteristics of entropy? See, entropy is a state function. Already you know what is state function. State function means this change in entropy delta S depends only on initial and final state and not on the path followed. Next point, entropy is extensive property. Entropy is extensive property. That means which depends on the mass or quantity of the substance, right? So entropy is a state function. It depends on only initial and final state. Say for example, this is the PV curve. Okay, so from this point to this point, say this point to this point, or I will draw like this. Say this point to this point. You can come directly through this, or you can go, this is A point, this is B point, or you can come this and this. Say this is C. So this and this, or you can come this and then this. Say this is D. Okay, from here then here. That means, see, the change is from A to B. Okay, entropy change, that is delta S for A to B, that is equal to entropy of state B minus entropy of state A. And that is equal to this path and this path, because it depends only on the initial and final state. So this one I can write it as SB minus SA A, this path, I can write it as this path plus this path. That means S entropy at C minus entropy at A, that is this path, and then this one, that is entropy at B minus entropy at C. Or we can write again this SB minus SA, that is the delta S of A to B. That we can write it how? This path, that is SD minus SA plus this and this, that is SB minus SD. Okay, because entropy is a state function. Whatever path you follow, this change in entropy, that will depend only on the initial and final state and not on the path followed. Okay. Now coming to definition and formulation. Okay. So coming to definition and formulation. Entropy mathematical formulation will derive from Carnot cycle. In Carnot cycle, you have seen that this efficiency eta, that is equal to what we have seen, Q2 minus Q1. Q2 is the heat absorbed from the high temperature source, Q1 heat released to the low temperature sink, divided by Q2 is equal to T2 minus T1 by T2. T2 is the temperature of the high temperature source, T1 is the temperature of the sink, that is low temperature. Right? So from this, what we can write? 1 minus Q1 by Q2, that is equal to 1 minus T1 by T2. Now this 1 cancel, minus minus cancel. Then what is left over? What we can write? That is Q1 by Q2 is equal to your T1 by T2. And from here I can write Q1 by T1 is equal to Q2 by T2, or we can write Q by T is constant. So this equation Q1 by T1 is equal to Q2 by T2, or Q by T is constant, right? Now this term, that is Q by T, what is Q by T? Q is the heat absorbed or heat released. Isothermally, heat absorption or release occurs in the isothermal condition, isothermal process, not in the adiabatic process. Isothermally and reversibly, because Carnot cycle all the steps are reversible, divided by temperature at which this heat exchange occur is known as the change in entropy, is equal to change in entropy. Okay. So what we can write from here? That is heat exchanged isothermally and reversibly divided by temperature at which heat exchange occurs is the change in entropy of the system that is delta S, right? Now, you know, in Carnot cycle, that is, in heat is absorbed from the high temperature source. Okay, so this Q2 is positive. Here heat is absorbed, right? So what we have seen here, Q2 by T2 is equal to Q1 by T1, right? Now Q2 is heat absorbed, so this is plus, we can write plus Q2 by T2 is equal to Q1 is heat released in the low temperature sink, so minus Q1 if I put the sign by T1. So from here what we can write, Q2 by T2 plus Q1 by T1 is equal to 0. Okay, what is the conclusion? So in Carnot cycle, the summation of all Q by T, this is equal to 0. Okay. Now, here, so entropy change in entropy, what we have observed that delta S, that is change in entropy, delta S is equal to Q by T, where Q is the heat exchange, right? Now, in Carnot cycle, all the steps are reversible. So, we write change in entropy is equal to Q reversible by T. So, this entropy change, either you write this way or you can write that change in entropy is the integration, that is sum of all the small steps, that is del Q reversible by T. Okay, that means this small change in entropy ds is equal to del Q reversible by T. What does it mean? Reversible process, you know, it takes place through a number of small steps. Okay, so each small steps del Q entropy changes del Q reversible by T. For each small step, this temperature is constant. Okay, but for different step, it is different. Okay, now if you take the sum of all the small steps, then you will get the finite change in entropy. Delta S for the entire process, right? Yeah. From this entropy formulation, one thing it is clear. See, entropy formulation is what? Delta S is equal to Q by T, or Q reversible by T, because in Carnot cycle all the steps are reversible. Fine. Q by T. Now look at here. For any system, if I consider two systems, say here temperature is T1 and here temperature is T2, right? And you are supplying same amount of heat, say Q amount of heat to here and same amount of heat to here. Then change in entropy here, and one condition, say T2 greater than T1, right? So here the change in entropy will be Q divided by T1. T1 is in the denominator, okay, where the temperature is less. Okay, so if the temperature of the system is less, then the change in entropy will be more. Okay, if the temperature is more, because it is in the denominator, if same amount of heat is absorbed, so if the temperature is more, Q by T will be less. That means change in entropy will be less. But if the temperature is high, entropy of the system will be high, but change in entropy will be less. If temperature is low, entropy of the system will be low. Okay, but the change in entropy will be high. Okay, so here if it is delta S1, so for this system, if I consider change in entropy delta S1 will be is equal to Q by T1, and for this system delta S2, for this one it is delta S2, for this it is Q by T2. I told that same amount of heat is supplied or absorbed, whatever it is. So, though it is in low temperature, but change in entropy here it will be more, because T1 is in the denominator. So, delta S1 will be greater than delta S2. Okay. And now, one more point you should remember. Before that, one thing I tell you, what is the unit of entropy? Okay, entropy means here it is entropy change, because I told you, no, we can measure only the change in entropy. So delta S, that will be is equal to Q reversible by T. Q means joules or calorie. So if it is in joules divided by T, Kelvin, then this entropy will be joules per Kelvin per mole. It is for 1 mole. And this is known as the EU, that is entropy unit. Okay. Or it may be, or delta S you can express in terms of, say, calorie by Kelvin. That means calorie per Kelvin and per mole. So this is the unit of entropy. Okay. Now, for any process, we just consider the entropy change of the system plus entropy change of the surroundings, which is equal to the entropy change of the universe. Okay. So, when we'll just predict whether the process is spontaneous or not, we just consider, remember this point, we will consider the entropy, not only the entropy change of the system, entropy change of the system plus surroundings. Okay. When the entropy change of the system plus surrounding, that is universe, is greater than 0, then it is spontaneous. Okay. So, in the next video, I will show you why entropy is a state function, right? So, we'll come to the end. Thank you.